Good morning, everybody. Welcome to Dynamics. Today we are covering from our Moodle page lecture number 8. We're going to be talking about section 12.2. Now our lecture today and our next lecture 9 are sort of intimately tied with each other. So we'll talk a little bit about orbital mechanics from the primer, which is available to you in these two files, and then we will also talk about section 12.2 in the book. So the presentation is a mixture of those two things for the next two lectures. Having said that, let's take a look at the subject matter of section 12.2 in the textbook, and I'll just bring in some of the ideas from the primer as we move forward. Section 12.2 talks about angular momentum and orbital motion. Now, your authors start out talking a little bit about angular momentum and the rate of change of angular momentum. But basically, angular momentum is defined as a moment of a moment. So I'm going to spend just a very short amount of time talking about the most general, the moment of momentum is what I should say. Sorry. I'm just going to take a minute about talking about what this is physically, and then I'm going to drop into our most important application for this, which is orbital mechanics, and some of the simplifying assumptions that we can make when we're talking about orbital mechanics. But basically, if we have a particle, which we can just call P, and P is moving in some fashion along a path, whether it's curved or straight, and we know that it's moving at some velocity, we know that its momentum, or the vector L, is defined as being the mass times the vector velocity. Well, if we take some point O as the origin, and we consider the distance from that point, r, not just a distance, but it's a vector, so it's a distance in a particular direction, and we take the vector r and we cross it with the vector L, or mv, just determined to do that, right? We get a quantity which is called the angular momentum about point 0. Now, it's very important to notice that HO is defined about some point. So in other words, you can't really refer to the angular momentum of P unless you talk about its angular momentum about O of P. Because if you think about it, if we had a different point, if we were taking it about, say, O prime, which is up here, we would have a different R. We would still have the same MV, but we could call this R prime. So we could say that H sub O prime is equal to R prime cross MV, and that these two quantities are not equal to each other. And that's just something I point out because it's a relatively common misconception, or sort of a it's an oversimplification that is in fact incorrect. So angular momentum must be defined about a point. Now, in terms of practical application, when we start talking about orbital mechanics, and I bet you're going to be able to answer this without doing any math at all, if you have a satellite P and it is in orbit, whether that orbit is circular or elliptical, about some point O. What is that point? It's whatever it's in orbit about, right? So like if it's a satellite in orbit above the Earth, O is the Earth, right? And if it's a planet orbiting the sun, O is the sun, and so forth. So in orbital mechanics, the O is inherently known as or defined as the object about which P is orbiting. So I think this is sometimes why people get this concept a little confused, because angular momentum is actually a very general concept. And in everyday life, if you have planetary gears, or you have a double Ferris wheel or something like that, the point of the rotation or the point of the orbit is not clearly defined. But when you have orbital mechanics, it is. And so sometimes I think people sort of back extrapolate it and say things like angular momentum is conserved. Well, angular momentum is not conserved except under a very specific case, which happens to be a hugely applicable case, which is orbiting bodies. But it's not in general conserved. So we'll talk about that in just a minute. So if HO, or the angular momentum about some point O, is defined as being the cross product of R times mv, we can think about R in three-dimensional space as being R sub xi, R sub yj, R sub zk. And we can think about this as being m times v sub xi plus v sub yj plus v sub zk. Right. We can further think about the magnitude of that vector, not the direction, but just the magnitude, as being r times mv times the sine of the angle between them. Or actually, it's the extension angle. So if we look back at this diagram, we can think about this angle as being phi. So in other words, we're just projecting a perpendicular, aren't we? Because the sine is the opposite side. So we're taking a perpendicular, and we can get the magnitude of that cross product. But if we really are going to execute a cross product and write H sub O as the vector that it really is, we need to evaluate a determinant that's constructed of the components of those vectors. X, Y, Z. Sorry, I keep wanting to put K there, but of course that's silly. And then we could put mv sub x, mv sub y, mv sub z. All right, and then we need to evaluate that determinant. So as a reminder, if you've ever done these by hand or if you've not, what you do is you take a multiplier row or column, but the best general rule of thumb is to use the multiplier row as the top, although you could use any. If you have a lot of zeros, sometimes it's easier to use a different row or column. But you're going to break this down into little baby matrices or little baby determinants based on what's left over by crossing out the row and column of each of these items. So the way that it works from linear algebra is the first item, item 1, 1, first column, first row, has the same sign, so we assign it positive. Then we alternate between same and opposite signs for the other elements. And then we multiply by the small determinant left over when we cross out the row and column of that item. So J, we would cross out the row and column of that item. So in other words, there's that. So here we have R sub x, R sub z, mvx, and mvz. And last but not least, we would have k times what's left over when we cross out the row and column that that item exists in, R sub x, R sub y, mvx, mvz, right? And then the way that we solve a 2 by 2 determinant or to evaluate it is to multiply the elements on this crisscross and subtract the elements on this crisscross. So in other words, this is I times the quantity RYMVZ minus RZMVY. So this would be the x component of my angular momentum. Then we have a minus, or change of sign, times RXMVZ minus RZMVX, and then plus k times the evaluated determinant here, R sub x mvz minus R sub y mvx. All right, now there's a couple things I just want you to notice about that. One of the reasons that it's easier often to break this out using the first row as your multiplier row is that then you have all of your I stuff gathered together, all of your J stuff gathered together, and all of your K stuff. If you have zeros in some of your rows or columns, sometimes it would be easier to choose that row or column, because zero, if there's a zero out here, then the whole thing is zero, right? 0 times 0 is 0 times anything is still 0. So it can make your math a little bit easier, but this will gather things up in a very reliable way. The other thing I wanted to point out is that the stuff in the I component is all comprised of Y's and Z's. The stuff in the J component, in the J direction or the Y direction, is all X's and Z's, and the stuff in the Z component, in the Z direction, are all X's, and that should be a Y. See, I've already made a mistake. So this should be VY, and that should be VY. Okay? So, in other words, everything is mutually perpendicular, which is sort of the hallmark of a cross product, right? We know that every cross product is perpendicular to the plane of the two vectors, the plane that the two vectors that comprise the cross product make. So what we're talking about is an axis of spin. Just like in physics, when you do the right-hand rule, IJK, everything is perpendicular. So when you cross R and MV, the cross product is going to be, the cross product or the angular momentum is going to be perpendicular. Now, that means that the way I have this drawn, where R and MV are in the XY plane, that means that my H is going to be purely, my H about 0 is going to be purely Z. So when you go back and you look at this, it will turn out that this will be 0, this will be 0, and this will have some numerical value. Doing these, it's really easy to make a little mistake. So it's much better to use an equation solver. You can solve this using Excel or MATLAB or probably your calculator, but it's a long, tedious project, you know, to do cross products. I mean, it's not without value in and of itself, but it can be a little bit strange. All right, so why do we care about this? Well, there's a lot of applications for angular momentum, but one of them is this. If we go back to our original thought here, and if we think about a satellite orbiting a planet, it turns out that our force will always be directed in the normal direction. In other words, our force is directed toward the center of the planet. and there will be no other particular forces acting on an object orbiting in space. For example, if we have a satellite above the Earth, the only thing that's really keeping it in orbit, if it's outside of the Earth's gravitational field, if it's just, well, it's not really outside, but if it's not having surface effects from the Earth, everything about it is operating in a central force. And when you have H sub O acting under a central force, it is conserved. Angular momentum is conserved in this very specific case. But the reason that it's important is because the specific case has such a broad range of applications. But in general, angular momentum is not conserved, and in general, you have to clearly define the point that you're taking the angular momentum about. It's just that those two things simplify in the case of orbital mechanics. All right. So what that means is that if you have any object orbiting in a plane, which very nearly orbital objects will remain within a particular plane in space, that the angular momentum will always be perpendicular. So it represents a pure axis of rotation, so to speak, for that moment of the momentum. When we talk about orbital mechanics, this is always true. R crossed with mv is equal to h sub o. But often using polar coordinates or normal tangential coordinates will be more useful. But with polar coordinates, it turns out that little h, I should probably put this, h means r cross mv. Little h is just r cross v. In other words, little h just represents the intensive property of angular momentum, or angular momentum per unit mass. And little h then in polar coordinates can be expressed as r squared theta dot, or capital H could be m r squared theta dot. All right, and both of these are written as values. All right, now on page 765 of your textbook, they talk about the conservation of angular momentum. That's equation 12.22. And it says that R crossed mv is equal to h sub o is equal to a constant. Now, it's important just to note, I'm bringing this up just to avoid the pitfall, because when you're doing your homework, if you have a non-central force, non-orbital situation, for example, you'll say, oh, this is a constant, and this simplifies my life quite a bit. And the answer is only under certain conditions. So when you take a look at that equation, make sure that you're satisfying the conditions of that equation, which is central force, orbital mechanics or such. So it says that, if you read underneath it, it follows that the position vector r of a particle p must be perpendicular to a constant vector h0. Thus, a particle under a central force moves in a fixed plane perpendicular to h sub o. That's exactly what we're talking about. M, v, r are in a plane. Everything's acting under a central force. Then h sub o is perpendicular and is constant or is conserved. So it's just something you need to keep in mind. All right, now the next part of section 12.2 just breaks down and discusses, which is a direct consequence of angular momentum conservation under a central force. But we talk about Newton's law of universal gravitation, which is extraordinarily useful. Gravitation. There we go. And it tells us that the magnitude of the force of gravity is equal to capital G. Which we're going to talk about in just a minute. Capital G is not equal to little g. In other words, little g is 9.81 meters per second squared, or 32.2 feet per second squared. G is neither 9.8, 3.2, 32.2, nor is it in units, in dimensions of length per time squared. So we're going to talk about what it is in just a minute. Times a capital M times a little m over an r squared. Well, this is a unit of force, and it's basically the force of gravity, but basically it's the force of attraction between any two bodies. A capital M is the larger mass. Little m is the smaller mass. And r is the distance between the mass centers of M and M. All right, now what this means is, just to fill in the blanks, is that if you have a person standing on the earth, the mass of the earth is capital M. The mass of the person is little m. And r is the distance between the person and the mass center of the earth, which is roughly the center of the earth, or r is the radius of the earth, more or less. That F will be the force of attraction between those two objects, which is actually the person's weight. Now, what this really brings out that's very interesting is that the person is attracted to the earth with a force, but the earth is also attracted to the person with the same force in the opposite direction, right? So that's kind of an interesting effect. This is equally applicable for the earth with the moon, not to scale, right? Rotating about it. So this time r is the distance between the earth and the moon. Little m would be the mass of the moon. Big M would be the mass of the earth. And F would be the force of attraction between the two. In other words, why does the moon stay in orbit? Because it's attracted to the earth. Yes?
So if it's not a sphere, if it's like some weird shape, you have to find like the center of gravity to find out r?
Yeah, you do. And that is an excellent discussion. But yes, and this is actually, I don't know if this is exactly applicable, but I'm going to say it anyway. It's somewhat applicable. Depending on where you are on Earth, do you remember from surveying that, you don't have to, but I'll quiz you anyway. Do you remember what we referred to the shape of the Earth as being? It's not really a sphere. Yeah, something like that, exactly. It's an oblate spheroid. Okay, and what that means is it's a little bit pear-shaped. It's oblate, which means flattened, and spheroid meaning kind of like a sphere. So the southern hemisphere of the Earth is actually statistically significantly larger than the northern hemisphere, and there's some flattening at the poles. So the other part that's kind of interesting is we have this iron nickel core that we call the center, right? But the distance, say, from here to the center to here is going to be a little bit different. We also have a magnetic axis, and there is underneath, like, the continental shield of North America in far northern Canada, there's a big magnetite body up there that pulls compasses off. So yeah, so the center of the Earth is not, there's a difference. It's called the centroid, which is the geometric center, and the center of mass, which is really what we're talking about, or the center of gravity. And so we're really talking about the center of mass here. So there are things that pull it out a little bit. But for general purposes, we just think about the center. But if you were doing precise calculations and you had something that was quite irregular, you would absolutely have to take those things into account. And if it was spinning, it gets even more fun. Yeah. So, so we won't do that in here, but you've got a couple different things going on when that goes on. And the other thing, I'll, sometimes, just for the sake of general interest here, the idea of gravity is really well defined, but we don't really, it appears if you look at relativity, that gravity is actually a little different than we view it to be. So it's really, it appears that mass sort of warps space-time. Space and time are not as separate as we, as humans perceive it to be. So we have a warpage. And so this equation of Newton's law of gravitation describes an effect very well at relatively slow speeds. And by that, I mean pretty much anything on Earth. But if you get close to the speed of light, there are some changes to that as well. And really right now for man-made, well, I guess there's really, I'll say that man-made technology. It sounds kind of redundant because I don't know who else has technology. Maybe spacemen, but I don't know anything. They haven't given me their primer yet, so I don't know. But if you look at technology on the Earth, there's really only one type of technology that requires a correction for relativity, which are GPS satellites. So, and it's not that any of them move close to the speed of light. It's that things on the Earth and things spinning in orbit will have enough, the relative speed between them gets close enough to the speed of light that we need to make slight corrections to make everything very, very accurate. But to my knowledge, I guess the armed army men and the high top secret guys in the military may have some stuff that they correct for relativity too, but once again, they haven't let me in on their secrets. But I do know for a fact that you have to correct satellite data and GPS data to relativity. But for us as engineers building bridges and steamships and trains and conveyor belts and curbs and gutters, this is not a big deal. So anyway, it's interesting, but it doesn't affect our design work at this particular point. And Newton was pretty much a genius, in my opinion, as was Einstein, as was Tesla. I mean, we've had some pretty amazing thinkers at strange points in our history. And Newton was definitely one of them, but he was also a man of his time. He was a man ahead of his time, but he was ahead of his time. You know, so his science was based on observations. And he also added to a lot of stuff about Kepler's law, which is orbital mechanics, which is really strange because he really was visionary in some of those pursuits. But this is based on observation. And it turns out that capital G, which is called the universal constant of gravitation, has a value of 66.73 plus or minus 0.03, which is just the tolerance, times 10 to the negative 12th. And the units are very different than dimensions of length per time squared. But basically, it's mass to the third, in this case, or excuse me, length to the third, meters to the third, per kilogram second squared in SI units. and in English units, 34.4 times 10 to the negative ninth. The unit here, of course, would be feet. This must be changed to pounds. Feet to the fourth times pound second to the fourth. Okay, and at first blush, those don't look like they are dimensionally equivalent until you realize that kilogram is a measure of mass, pound is a measure of force. So when you use F equals ma to convert between those two, or Newton's second law of motion, then they become dimensionally equivalent at that point. Yes?
So that's feet to the fourth?
Yeah, feet to the fourth. See, that's what I was saying, because we have meters to the third, feet to the fourth. But this is kilograms in mass, this is pounds in force or weight. So if we change this into slugs, this would be feet to the third, and this would be seconds to the second squared. Excellent question. So you guys are awfully smart. All right, so the rest of this chapter just talks a little bit about the relationship between universal gravitation constant capital G and Earth's gravitational constant G. And there are actually some good problems that you can work out with this, but basically there's a relationship that will reduce from this work that tells us that capital G times m is equal to little g times r squared, or that little g is equal to gm over r squared. So you can see that little g on the Earth is going to be dependent on the size of the Earth and the mass of the Earth, and the Moon, which is quite a bit smaller, for example, is going to have the same idea, except for we have a different mass and we have a different r. So, yeah.
So was the big R and little r the same thing?
Oh, here? Yes, absolutely. This, let's see. Did I put a little, I did use a little r the first time. And you know, yeah, but it can be, okay, this big R can be two different things, and little r can be between two bodies, like a human being on the surface, or we can be talking about the r between an orbiting body and the center of mass. But the answer is yes. So it just depends on what your problem setup is. But yeah, and your authors do that. It wasn't just me. The way that your authors have it set up here, they're talking about specifically the mass of the Earth and the radius of the Earth. So they make a variable change at that point because they're talking specifically about the mass of the Earth, and then this would be little g of the Earth. But you could use this equation with the mass of Mars and the radius of Mars and get the gravitational constant on Mars as well. Yeah, very good question. All right, I was just going to see. All right, so I think we're going to stop there today. That's all of the material from section 12.2, and I will assign you just a couple of general problems that are not involved with orbital mechanics but are involved with maybe different sets of units in order to just work out a couple of problems. Then on Wednesday, we'll talk specifically about orbital mechanics and make these applications for bodies in orbit. And then Friday, we have a homework assignment due, which if you're keeping up, that would be great. But of course, I will accept that throughout the weekend. And then we do have a quiz that'll just be a one-problem quiz. It's open book. You can't even see this. Sorry about that. Let me put the right one up here on the screen. So the homework is due Friday. The quiz is also due Friday, but I've opened it up till 11:59 p.m. on Saturday if you prefer to take it on Saturday. And it's going to just be one problem, and it's timed but what you do is, it's a 5-part problem. What I'm really trying to do is to get you used to doing problems the way that you'll need to do them on the exam. So, so it'll be timed, and you'll fill in some answers, and then you'll email it to me within a particular period. With time, it'll be 45 minutes or an hour. But once you open it up, you're committed. So you have that amount of time to do the quiz, and then email me your work. Okay? And we'll talk about that a little bit more on Wednesday. All right? Well, thanks, guys. That's it for today. And we will get back to it and finish up Chapter 12 on Wednesday. So let me know if you have any questions. Like I said, I'll post a couple of homework problems. That will be general angular momentum problems, and then we'll talk specifically about orbital mechanics on Wednesday. So we'll see you then.